All right, so here's a little bit of history. Lambda Calculus is a formal mathematical system. It's also the simplest possible programming language. It was intended, it was designed or conceived in exactly the same context that the Turing machine was invented, which is this idea of understanding what functions and computation really are, and how can you compute, what are the limits of computability, and what does it mean to actually compute a function given an input argument. So, and how can you automate, basically, and how can you automate the computation of functions? So that was exactly the same goal as the Turing machine. And coincidentally, it was this calculus was described in a paper in exactly the same year. That's the Turing paper. So these two papers are 2 months apart from each other. It's really crazy. And so this one was written by Alonzo Church. Let me see if I link it. Yeah, I link it from this week's syllabus here. So I would encourage you to read Church's Lambda Calculus, although this one is even harder to understand than the Turing machine paper. This one is a little kind of difficult. It's a lot more mathematical than the Turing machine paper. So I am going to try to explain what Lambda Calculus is in a plain language, and in always coming back to what's the goal of things rather than staying in very abstract terms. And you will see here and there that how it connects to the things that you already know about programming. So a little warning though, that it may seem, the Lambda Calculus may seem trivial or irrelevant now, but and it may remind you of very obscure programming languages, like there's a niche of programming languages that people do just for fun. Like there's a whole programming language that is entirely made up of white space. I don't know if you have ever come into that language. It's basically, you don't see the program because it's just white space. It's the space character, the tabs. So it's basically unprintable characters that you don't see. And you have a programming language that is entirely made of that. And there's another programming language called Brain Bleep that is with incomprehensible characters too. That is, again, it's a Turing complete programming language. You can program anything in it. So the Lambda Calculus may seem like a toy language too. But it had a tremendous influence in programming languages in general. And I think what's the interesting, crazy thing is that its influence had such a long arc that I think we're only seeing the effects of the Lambda Calculus in the world, right, in the real world, quote unquote, recently. Okay, as of the previous 10 years or so, when functional programming started to become the target of a lot of attention from the software engineering point of view. But this whole comes back from 1936, and it has always been there. There's always a very sort of niche research community that has always been attracted to the potential of the Lambda Calculus and what the Lambda Calculus really kind of means, because it's really profound if you care to think about it, this weekend, for example, because it's really, really cool. But basically, the chain of reaction here is that Lambda Calculus influenced Lisp. So Lisp was a language that was designed in the beginning of the 1960s by John McCarthy at MIT. And it was basically an implementation of the Lambda Calculus. Okay, it was very much kind of influenced by trying to bring to life the ideas of Lambda Calculus in the form of a programming language, a programming system. And then, of course, Lisp became, a gigantic monster that had everything, and everything was invented in Lisp practically. Everything in programming was invented in context of Lisp, and it influenced everything. Okay, Lisp had also a tremendous influence in all programming languages, including the imperative ones. And as I mentioned briefly the other lecture, Lisp had a bad reputation of being slow for a long time, and it was slow. I mean, if that reputation was well deserved. It was much slower than the languages that were, you know, programming the machine directly, things like C and stuff like that. Until a lot of optimizations came along, but nevertheless, the things that the ideas and the concepts that were in Lisp had a tremendous influence on everything. So, for example, garbage collection, automatic garbage collection, right? That was in Lisp from day one. Okay, so this idea that you manipulate memory, that you allocate memory, and then you have to free it again, there was no such thing in Lisp, right? Because there's no such thing in Lambda Calculus. So memory doesn't exist in Lambda Calculus. And so in order to be able to do the Lambda, functional programming in a finite memory machine, the only way is to have some sort of an automatic garbage collection. And so garbage collection was invented and developed in the context of functional programming, like Lisp. And then it made its way a few decades later into the object-oriented programming languages, and it's an very critical part of the old modern programming languages that have automatic garbage collection. But not only garbage collection. I mean, it had a lot of influence in everything else. You know, as we go along this course, I will point out different things here and there. They were invented all in the context of Lisp. It's really unbelievable, the things that were developed in the context of Lisp. So just the historical context in the early 60s when Lisp came around is we were, assembly like Fortran, COBOL, unstructured programming, Go, galore. And suddenly there was this language developed at MIT by academics that had absolutely nothing, no similarities whatsoever with what people were doing in programming. It was completely different. There's no memory, there's no variables, there's nothing of that sort. And so it became an attraction for people in universities, definitely, in certain universities at least, that had a certain inclination for more, mathematical systems. For AI, it became the language of AI at the time, kind of reason-based AI. But for all the kind of practical and commercial applications, this Lisp never really made it big. At least not as big as the main competitor in the 70s, which was C, right? And the imperative languages that were going around because they were faster. And because people they were more familiar to a lot of programmers, as I said, because the Turing machine had an influence, and imperative programming languages kind of got a head start, basically. They got a head start in computers. And so that's what people were more familiar with. So that's the context of Lambda Calculus. But so let me start from the beginning. What is the calculus? And these are kind of really interesting abstract questions that you may want to kind of research a little bit during this weekend. A calculus is a branch of mathematics that deals with the limits and the differentiation and integration of functions of one or more variables. So, it's basically integrals, differential equations, limits of things. It's the stuff that we learn in high school and then maybe a little bit more in college. So that's a branch of mathematics. But basically, the real definition of a calculus, if you think about it, it's just a bunch of rules for manipulating symbols. Okay, so go back. It may take you some time to really understand what I'm saying, but go back to your lessons that you learned about integrals, for example, okay, or differential equations or something. But let's talk about integrals. So in an integral, when you want to integrate some function, the way that you express the integral is you express, the integral symbol there's some beginning at the bottom, that's some end at the top, there's the function then that follows, and then there's the d, whatever, x, you know, the little increments that you want to differentiate with. And so you are given a bunch of symbols that the mathematicians have converged to define the integral, okay, of some function. And then to actually calculate, to compute the integral of a function, then there's a bunch of rules that we learn, right, in college or whatever, that, you know, I don't remember anymore. But basically, there's a bunch of rules, and this is the algorithms, that tell you how to transform those symbols into other symbols, so that at the end, you get the actual integral of a function over, you know, over x or whatever, right? I don't know how many of you remember the actual algorithm, but basically if you want to integrate, you know, x squared between 2 and 10 on the x, there's some formula that I don't remember. Basically what it is you basically, you have x is a symbol, you know, the square is a symbol, the dx is a symbol, and then there's the limits over there, and then there's a bunch of the manipulation of the symbols, replacing numbers, replacing symbols by numbers, and then doing some basic operations like multiplication and subtraction and stuff like that. So we're basically manipulating the symbols, and at the end you get a number of some sort, right? That's what basically, at the bottom, at the most abstract sense, a calculus is the manipulation of symbols. That's what it is. And we start with a formula, you know, with an expression that means, for example, the integration of something, and we end up with another expression, which is typically a number, or it could be another function, right? That's basically what it is. And we learn how to manipulate those symbols. So people give meaning to these symbols, but it's not part of the calculus. So, you know, when physicists use the integral to denote some physical property of some body, you know, some movement of some planets or whatever, it's this extra meaning that people give, but the calculus itself doesn't care whether it's a planet going around, whether it's whatever, some stock market, or it doesn't care. It's just, you know, the calculus is just the symbolic manipulation of those symbols. So the differential calculus is a bunch of rules for manipulating symbols. There's an interpretation of those symbols in physics, you know, slopes, stock markets, and other stuff. But the interpretation is us who give it to us, right? So that's the first kind of eye-opening thing that, at least for me, you know, when I learned calculus, it seemed like it was sort of a ground truth, right? That there's, this is the ground truth, it's mathematics, right? This is what you do. But then you realize when you start reading about Lambda calculus, it actually goes deeper and completely reconstructs the truth that we learned in college about calculus. It's saying that it's just a bunch of symbols, right? And it's us who give the meaning to those symbols. So that's the first kind of, oh my God, what's going on in here? My ground is being shaken. So, all right, so the Lambda calculus, what is the Lambda calculus? So in the context of the Lambda calculus, yet another calculus, meaning that it's a system for manipulating symbols, all right? And in fact, it's the most universal and the most basic and the most symbol system for manipulating symbols. Okay, it's a system that when you manipulate symbols like this, you can manipulate any calculus. That's the absolutely crazy thing about the Lambda calculus. It's sort of the original language in a way. Okay, if you read some sci-fi movies about original languages and stuff. But if there is one, that's definitely the Lambda calculus would be it. So let me tell you what Lambda calculus is. So curious thing, there's only 3 rules. Okay, let's start with an interesting thing that there's number 3. So it's an interesting thing. So there's 3 rules. There's 3 things in Lambda calculus, and this is using a notation in BNF, you know, the traditional notation for denoting syntactical rules. It doesn't matter. Basically, what this means here is that this little language, this little symbolic system, has three things. There's only three things in this world. There's the x, okay, some variable. X, some variable. Basically, there are variables. There are things that vary. There are abstractions, okay. And I will tell you more about what abstractions are, but they are denoted like this. That's the lambda symbol, lambda Greek letter, followed by a variable, right? And then a dot separating these two things, and then an M, which is a rule, a term of this language, something else of this language, okay? So M is something else, something of this language, right? So this is an abstraction. I'll tell you a little bit more about that. And the next one is application. So what that means is this is the application of an abstraction M to something, okay? So the application of something of this language to something else of this language. Now let me just, there's nothing else. So let me just back up a little bit. The way that you have to read this, okay, the abstraction is essentially a function definition. It's actually specifically an anonymous function definition. It's functions without names. Okay, it's a function that takes one argument, and then the M denotes the body of the function. Okay, so the way that you in modern programming, the way that you have to parse this is that the lambda is some symbol that defines a function or something like that. The X is the argument, and then this thing here is the body of the function. All right, and this third rule over here is the function call. This is when you actually call the function, all right, with some argument. So the M on the left is supposed to be the function definition, and it's a lambda because there's no names. And then the M on the right is supposed to be something of the language too, okay? So there are basically, so let me back, what this calculus says, the system of symbolic manipulation says, is that there's only three things there in the world, okay? Let me put it like that. There's only three things in the world. There's things that vary, okay? There's abstractions of things that vary with which we can do something. And then there are applications of those abstractions to things of the language of this world. Okay, there's only these three things. There's nothing else. There's no numbers, okay, which is crazy if you think that this is in the context of mathematics. Okay, there's no numbers. No arithmetic operations. There's no addition, no multiplication, nothing of that sort. There are no loops, nothing. There's only these three rules, which is anonymous, variables, anonymous functions, and the application of anonymous functions to something that you give to them to apply. Okay, and hold on, this may be a little crazy. It's going to become a little bit less confusing in a few slides. But I haven't given yet the rules of operation of this calculus. How do you manipulate the symbols? This is just the grammar, just what this world considers that, what does it exist in this world? It's just variables, function definitions, and function applications. That's all. All right, so basically, just a reminder that this is basically, the lambda. If you do it like this in the notation of the lambda calculus, in the modern programming world, you would see it like a function x with the body m. Okay, m being something of this language too, and lm, for example, something like this. Apply the function L to M, whatever it is, okay? And all of these things have to be lambdas because that's the only thing that exists in this calculus. Okay, clear on the syntax? Well, the syntaxes can be confusing. The original notation for the lambda calculus can be very confusing. So a little bit of terminology before I explain the operation of this symbolic manipulation system. Bound variables. So bound variables are these x's. Basically, they're the parameters. Okay, the parameters of a function are called bound variables, and they are bound to the lambda. That's what it means. The lambda owns them. So if they are variables, but they are not complete variables out there, they are bound to a particular abstraction. Okay, that's what it means. So the binding operation, the lambda, binds the variable in the lambda term xn. So they're not completely crazy. They're just bound right there. It means that x means something within m. All right, that's what it means. So m is called the scope of x, and x is said to be a bound variable or a parameter. You know, in normal terms, we call it a parameter. Free variables are symbols that are not bound. So free variables are, if you end up, you know, if you just do some symbolic manipulation in lambda calculus, and then you end up at the end with something that is not a lambda, then you end up with a free variable that's not bound to anything. It's just a variable, right? So renaming of, so here's, I'm going to move now to some of the operational rules of the lambda calculus. So I've presented just the syntax, okay, the concepts of lambda calculus and the syntax. Now I'm going to explain how the computation actually unfolds. How do you manipulate the symbols in this lambda calculus, okay? So there's basically just two rules, all right? Just two rules, operational rules. The first one is the alpha conversion. That is basically the renaming operation, which you are all very familiar with. It seems totally intuitive, but the church had to spell this out. This was important. It's an important thing of symbol manipulation, which is the following. That if you have a function definition like this, so lambda x and then some body, this is exactly the same as renaming x to y, so renaming the variable, as long as inside the body you also rename all occurrences of x with the new name, right? So this is pretty intuitive. If you have, you know, if you in Python you declare a function f that takes the argument x, for example, and then you use x in the body, it's exactly the same function. If instead of x you rename the x to y, you just have to remember to rename all the occurrences of x with y. Okay, so the renaming operation is a symbolic manipulation, right? And it's one of the basic symbolic manipulations in lambda calculus. You can rename, you can basically rename things and it means the same, as long as you rename it consistently in the method. All right, now we're going to the most important operational rule, which is called the beta reduction. Okay, this is the core of symbolic manipulation in lambda calculus. This is how you actually compute in lambda calculus. Here's how it goes. So it's basically how do you evaluate a function, okay? So if you have a lambda, an anonymous function like this, and you apply this lambda, you give it some concrete argument, okay? How do you do this? Now we know, you know, this is, you know, the bread and butter of programming. If you call a function with an argument, and what that really means is that you basically inject this argument E2, you replace it, the x, with the value that you give it, and wherever you have x in E1, you put E2, right? So basically you replace every x in E1 with E2, and you evaluate the resulting term, and you return the results of the evaluation. So this is basically a beta reduction. What this means is that if you have a function application like this, you have a lambda, and then you apply this lambda, you call the function with a concrete argument. And what is the way that you are supposed to manipulate these symbols is that you replace the x with E2, and then everywhere in E1 where x exists, you put E2. Right? That's the beta reduction. So a term that can be beta redux is a redux. It doesn't matter. This is basically what I'm saying is that this is how computation actually occurs in the lambda calculus, by doing beta reduction. Okay, how do you call functions? It's exactly like this, by replacing symbols. If you think about it, even if you think in Python, okay, or C or C++ or whatever, Java, that's basically what's going on, right? You are replacing the concrete value of the argument. So with wherever you have the formal parameter, you're replacing that formal parameter with the concrete value that you pass it around. Especially if you have, look at the programming language as an interpretive system that you interpret at runtime. That's basically what's going on. You're replacing some symbols with other symbols consistently in the body of the method. So basically, functions in programming and function calls, okay, the concept of a function definition and a function call comes from the Lambda calculus, right? And what it means to call a function comes from the Lambda calculus. It's a funny thing that it's, that people were using subroutines and all of that stuff, blocks, and very kind of imperative style kind of things. And they sort of converge to the same thing eventually, but it has completely different roots, right? This comes from mathematics. It doesn't come from engineering. It comes from the idea of what does it mean to manipulate these symbols and be able to reduce, basically, which is compute. So basically, in the Lambda calculus, a computation is basically just pure symbolic manipulation. You take an expression, which is a lambda expression, okay, a sequence of lambda things, terms, and then you apply this reduction, the beta reduction, and at the end you get something, okay? And that something is the result of the computation. So it's basically just replacing some symbols with other symbols. It does not mean anything. It does not know about numbers. It doesn't know about sums. It doesn't know about multiplication. It doesn't know about anything. It just knows how to replace symbols with other symbols. That's all. Okay? And I keep emphasizing this because this just blew my mind. It will blow your mind when you realize what is going on. I guarantee you. All right, so now there's a little bit more of details. Hold on, let me close this door that is making an annoying noise. There's a little bit of details about how to parse these things because the lambda expressions written in the original syntax can be really difficult to read. So, the scope extends as far as the right as possible. So something like this is actually something like this. The parentheses are not original symbols in the Lambda calculus, but it makes it easier for us to parse. Function application is less associative in the original Lambda calculus. So X, Y, Z means first you apply X to Y, and then you apply the result to Z, right? Which again may not be super intuitive because we're now used to doing sort of the other way around. So now, all right. So let me now go into starting to build some concepts of programming that you are familiar with from these simple rules. Basically, let me recap. What we have here in Lambda Calculus are 3 syntactic rules and 2 operational rules. That's all. So in this world, there are variables, there are abstractions of variables, and there are applications of those abstractions to concrete values. All right? That's all there is. And now the way that we are going to compute is by doing this beta reduction, okay, which is function application, replacing symbols with other symbols. That's all there is. There's nothing else. So one thing that you may also know, the very first thing that you may notice is that in the original Lambda calculus, functions are just single argument functions. There are no functions with 2 arguments. So for example, if you wanted to calculate like the hypotenuse of a triangle, that's a typical example, right? You take the 2 sides, right, A and B, and you wanted to calculate the hypotenuse. Right? So you need a function that takes 2 arguments. There is no such thing in Lambda calculus. Okay? Literally, the functions in Lambda calculus take only 1 argument, not 2, not 3, just 1. And I'm going to say this many times. These very simple rules are capable of expressing everything in computing. Everything. You may think that I'm crazy, but it's true. So, first problem. Suppose that you want to express functions with 2 arguments, and you only have functions with 1 argument. All right. So before I even tell you, this has a name and everything. It's called carrying. Let me try to find. Let me go to REPL or something. All right. So suppose that you really wanted to have an hypotenuse that of A and B function. Oops. This hypotenuse A, B, and you know, normally would let's say something like return the square root or whatever it is, there you go, of A square plus, okay, Python, yeah, Python seems to have that, the square. No? What's the squiggle? Okay, I have to import some math or whatever. Does anybody remember what I need to import?
You have to import math.
Math, just like that.
And then run math.square root.
Right, okay. So suppose that you wanted to do this, and this, you know, then you would call it, you know, whatever, h of root r. All right, no such file main. Start. What did I do here? Okay, fine. I'll just do it here. All right, okay. So this works as you would expect. But now suppose that I tell you, here's a constraint. You cannot have functions with 2 arguments. All right, I want ideas for how am I going to do this if I cannot have a function of 2 arguments. So if I don't have a function of 2 arguments, means that I only have a function of 1 argument, right? What is this function going to do? Any ideas?
It will return another function.
Yeah, that's right. So you can return another function. Let's call it, let's give it names just to, for now. Okay, so let's define, you know, in Python, you can have inner functions in functions that called HH of B. And finally, this HH of B returns that thing over there. And this one returns HH. Yeah? Now this may be super trivial for a lot of people who are used to functional programming, and this may be super confusing for those of you who have never dealt with functional programming. But basically, what I have here is a function h that returns another function. It returns a function, it doesn't return a value, it just returns a function. And what this inner function does is that it returns the square root of both of these arguments. So if I want to call h now, I should probably call this h2, not to confuse things. So if I were to call h2, I have to give it just 1 argument, because it only returns 1 argument. And now, what does this return? It returns a function, right? So if it returns a function, I have to pass it another argument like this. All right? So let me paste this here for you to see that it works. Right? Is everybody following? Note that the form here is slightly different, okay? This one, you just have a function of 2 arguments, so you just pass it to 2 arguments. But this one, you have a function of 1 argument, And this one returns a function, so you have to call that inner function that is returned with the second argument. But at the end, you get the same thing. So basically, what I'm doing here is what's called carrying, okay, which is this technique that is perfectly capable of, given a system that takes only functions with only one argument, you can have functions with how many arguments you want by doing this kind of thing. Right? By always returning a function that then what it does, it gets the next argument. And if you would take 3 arguments, then that FHH would return yet another inner function that would get the third argument. Okay, is everybody following me? This is called carrying. Okay. This may or may not be useful. It's definitely useful as an intellectual exercise for those of you who are not very used to functional programming, because it is the bread and butter of functional programming. The bread and butter of functional programming is this idea that functions may return not just values, but they may return functions too. And you may pass functions as arguments. In fact, in functional programming, there is no difference between functions and values. It's the same thing. And this comes from the Lambda Calculus. That's the beauty of it, okay? I will show you how this comes from the Lambda Calculus. So basically, this is carrying, all right? So if this doesn't exist, then what you need to do is define a function that returns another function, and then that function takes the second argument, and then the body of that inner function does whatever it needs to be done with the two things, because both variables are bound, meaning that they are bound to some value, right? They are bound to some value, so you can do that computation. It's called carrying. So basically, what this means is that the multiple argument functions are just syntactic sugars, just convenience. You don't need to have multiple argument functions language. You can express multiple arguments with language with just one argument, perfectly fine, okay? It's just syntactic sugar, nothing else. It's not sort of basic or foundational or primitive. All right, so a programming language is not very useful. So I've explained to you the basics of, I tried to make the argument that the simple Lambda calculus with 3 syntactic rules and 2 operational rules is all you need to have a complete programming language, okay? Which may be really difficult to believe, okay? Because so the first thing is that how do you deal with numbers? In computation is all about numbers, right? Where's the number 1? There's no number 1 here. Where is this addition? There's no addition here. There's nothing, right? And the beauty of this is that it doesn't exist in the Lambda calculus because the Lambda calculus doesn't need it, but it can be constructed with the Lambda calculus. All of those things, numbers. Here's a profound philosophical, kind of finding of Lambda calculus, is that numbers, those primitive functions like sums, arithmetic, numbers in arithmetic are not primitive. Okay, that is, when I realized this, I thought that my world had collapsed. I had been told a lie, since first grade, that we're dealing with numbers and arithmetic, and suddenly what the Lambda calculus shows is there's nothing profound or basic about it at all. There's something else that's a lot more basic, which is the Lambda calculus and symbol manipulation. So let me tell you how to bring back things like numbers and booleans and conditionals and the things that make up language, right? The programming language and the normal language too. So the next thing that I'm going to show you is how to bring boolean values and conditionals, how to make them exist in the Lambda calculus. So, as I said, the Lambda calculus deals just with these basic simple symbol manipulations, but we can make things up. We can give meaning to things on top of it. So we can just say, for example, that true and false are essentially functions of 2 arguments. And now, okay, remember when I say functions of two arguments, it's already not a primitive thing, but we already know how to do that, right? Functions of two arguments are simply functions of one argument that returns other functions, right? That we know how to, so now I can say functions of two arguments, and you know what I mean, okay? So what is true and false? True and false are the true and false values. That we call them values, right? But they're not values. They're just interpretations. Okay, they're just things that we put on top of the Lambda calculus of anonymous functions. So what are true and false? We can say that true and false are functions of two arguments where the true value is when that function returns the first argument, and the false value is when that function returns the second argument. Okay, this is basically what I said is what's written here. So true and false are functions of two arguments, right? This is how you have to interpret this. Here's functions of two arguments, where true returns the first argument and false means that you return the second argument. Okay, let's just assume that. Something like a conditional, like if then else, might be something like this, that if you apply, it's basically a function of three arguments, which is the true clause, the false clause, and the, I'm sorry. It's a function of three arguments. The condition, the true clause, basically what happens when the condition is true, and the false clause, which is what happens when the condition is false. Okay, so basically, if and else is a function of three arguments like this. Okay, and basically, for example, if you say if and else true, B, otherwise C. Okay, if we want to say like this, if you want to say this, if you express this in the Lambda calculus, here's how it's going to look like. So if and else is a function of three arguments, but so here's the first argument, here's the second, here's the third. But this, if we say true, okay, true is this value, this lambda, okay, as by definition that we said it here. True is this. And then B and C is something else, okay? So this being true, the thing that we should get at the end should be B, right? If it would be false, the thing that we should get at the end should be C, right? So by the rules of true and false, and by the operation, you know, the beta reduction, indeed this is what happens, because we bind B to X, all right? We get lambda Y of B applied to C, and then we bind C to Y. There's no Y in here, so we get B. Same thing if we do, if false, then B else C. If this is false, then we bind C to X, we get this, because there's no X in here. And then we bind this, and then we replace Y by C, and we get C. It works, right? It's starting to look like a conditional that is capable of dealing with conditions of true and false, right? Now, before I continue, let me just make a meta comment over here that the Lambda calculus itself is super simple. We are now going into a next level, which is how to use the Lambda calculus to construct a programming language. Okay. So programming languages require things like, you know, multiple argument functions, conditionals, values of true and false, numbers and stuff like that. So that's where we are going. And all of that, you kind of have to sit and think a little bit about how to manipulate, how to construct those lambdas, those very simple lambdas, in order to do what you want. It's basically conventions, right? It's conventions that you kind of see, okay, this is going to do what I want, right? So you need to think a little bit. Somebody needed to think about how to express the behavior of conditionals in the Lambda calculus, right? And this is what it looks like. So if you have a true and a false that are functions of two arguments, that the true returns the first argument and the false returns the second argument, then you can have this behavior that is what you want out of conditionals. Then if it's true, then you return B. If it's false, you return C. Okay? It's a little bit like writing programs in the Turing machine, that you kind of have to think about how you're going to control the go left and go right, and what symbols you write in order to achieve what you want. All right, so there's a little bit more, there's a more complex conditional over here that you can read at home. But so let me talk about numbers. Numbers are really cool because, again, numbers don't exist in Lambda Calculus, but we can construct them. We can invent them on top of the Lambda Calculus. We can give meaning to these lambdas, to these abstractions, anonymous abstractions, in order to make sense for us, to do things that we are used to, like, for example, numbers and arithmetic. So how are we going to get numbers out of these crazy lambdas out here? So these are called the church numerals. The church, Alonzo Church invented this. So he was the one who proposed how to bring back numbers. Because of course, every first grader needs to have numbers. We absolutely need to have numbers. We cannot live without numbers. So we have to bring them back. So here's how it goes. The number 0 is a function of two. Actually, all the numbers are a function of two arguments. Okay, this is how you need to parse this. So numbers are functions of two arguments. They're all functions of two arguments. And I'm calling the first one F, just to remind myself that it has a special meaning, and the second one X. All right, just to remind them. So F typically denotes a function, and X typically denotes something else. Okay, so this means that I want a function. I want somebody to give me a function here, roughly. Okay, but it's just a convention to remind myself, to remind ourselves. But basically, a 0 and all the numbers are functions of two arguments. Okay, and so the number 0 is the 0 times applications of the function to the argument, to the second argument. So basically, you don't apply the function for 0. You just don't apply. So in other words, before I even continue, what are numbers? They count the number of function applications. This is our meaning. This is what we're putting on top. Okay, how many times are we applying that function? That's what numbers mean. So the number 1 is one-time application of the function f to the argument. The number 2 is 2 times application. The number 3 is 3 times application, etc. Okay, so if we have expressions that look like this, lambda expressions that look like this, then we have decided that these are numbers, at least sometimes, that we want these to be the integer numbers. Okay, this is by definition. We want this to be the integer numbers. It has a nice consistency to it. It basically counts the number of function applications. The function being also an argument here. Okay. So given that these are the integers, this is how we define the integers. How are we going to bring arithmetic back? We need sums and multiplications. We need all of that good stuff. So let me start with the simplest possible arithmetic function, which is a successor function. So given a number, it returns the next integer. Given an integer, it returns the next integer. Okay, so given a 3, it returns 4. Given a 4, it returns 5, etc. So here's how to do it. I'm just saying that this is the successor of n. So what is the successor of n? This is n, the first argument. It's another number. Here's a number, right? The numbers themselves, remember, are functions of two arguments, that applies f to n f x. Okay? Now, this didn't come out of there. Somebody, Church had to sit down and think very carefully about what exactly sequence of symbols he would put here, so to implement the successor function. Okay, you have to think, okay? It's still like writing a program in a Turing machine. You have to think. But so after he thought long and hard about it, he came to the conclusion that this actually implements a successor function. So let's try it out, okay? So let's try the successor function on the number 1 in the Lambda calculus. All right, so here's a successor function. All of this stuff, this is a successor function, okay? And this is the argument. This is 1, okay? This is the number 1. Remember, so the number 1 is a function of 2 arguments. One is supposed to be a function and one is something else that applies g to y once, right? Okay, so now let's go to the craziness of the Lambda calculus with a beta reduction. So I already have something wrong in, oh no, I don't have something wrong. Actually, this guy should be, the red thing should be a little bit more to that. But basically, this is the argument. This entire thing is the argument number 1. So this entire thing is going to bind to n, all right? So wherever we have n here, we're going to replace it by this expression, all right? So we had n over here. We got rid of the n here. And wherever it was the n here, we put the number 1 here, which is this thing over here, right? That's the beta reduction, the first beta reduction, okay? Now, let's see what else we do now. We apply f, right? So now remember, a function application is left associative. So now we have to apply this function to f, right? So now we're going to bind f to g, okay? So wherever g is, we put f, and we end up with this, okay? And finally, we apply this function to x. So we take x, wherever we had y, we replace it with x, and we end up with something like this. And voila, if you look at this, this is the number 2. It's a function of 2 arguments that is applying f twice. We have the number 2. And if you try it on the number 3, you will end up with the number 4. Okay, this is pretty wild. We're just doing symbolic manipulation with anonymous functions. That's all we have. It's anonymous functions. It just happens that we want to give some meaning to some of these anonymous functions. Okay, because we cannot live without some of these symbols that we've gotten used to, like numbers. There's more. So recursion. This is another funny one. This is a profound one, and I cannot say that I fully understand it. I see the beauty of it, but it takes, you know, deep thought to really understand the recursion in Lambda calculus. So here's the thing. What's the deal with recursion? That the recursion that we are used to, okay? If you go here to REPL, I can have a recursive function, for example, factorial of n, and that is basically, you know, if n less or equal to 1, you know, letting this return 1, else return factorial of n minus 1, something like this. I'm not even running. But so here's the thing that you probably never even thought about. When we learn recursion, when we have recursive functions, we typically have our functions in our normal programming world have names, right? So functions in our programming world that we are used to have names. So this function is called factorial. So if we want to recurse, our life is very simple. We just call it by name, right? We know its name. We just call it again, right? So functions have names in our world. In the Lambda calculus, functions do not have names. They are purely anonymous functions. They don't have names. Now, in Python, you also have anonymous functions, right? Everybody knows in Python or Java, whatever, you have the lambdas, right? Yes, so you could have, let's try to define, for those of you who know lambdas. Fact equals, you know, lambda of n, and now I leave you as an exercise. How can you define a recursive function, for example, factorial, with an anonymous function? Because you don't have name. What would you, you know, even if you could say, let me try to write this in it. 1 if n less or equal to 1, else, else what? Now what? What do we do? This is a mind-boggling thing. Like, if you don't have names, it looks like you cannot have recursion, because that thing that you want to call does not have a name. You would have to call yourself again. You would have to call this lambda, right? But you don't have a name to call it. The crazy thing is that you can express recursion even with anonymous functions, and this has been proven here in the Lambda Calculus. By, you know, again, somebody had to think long and hard about it. But basically, here's the thing: if you have an anonymous function, and this is what I was kind of writing over there, you don't have this. You know, it's a free variable. We don't have, this function does not have a name, so we cannot call it like this. So comes the Y, what's called the Y Combinator, which many of you know as a startup incubator somewhere in San Francisco, maybe some of you know. But the Y Combinator is actually part of the Lambda Calculus. It's a very important and integral part of the Lambda Calculus, which is a combination of lambda functions. Okay, so it's a lambda expression that's called a function combinator, that is capable of creating recursion out of thin air, as far as I can tell. Okay, it's totally crazy. So here's in the next lecture, I will try to invent the Y Combinator for you as best as I can. But for now, just let me tell you that the Y Combinator is this expression, this lambda expression. Just take this for truth. Okay. So if you have a Y Combinator that looks like this, and you apply this combinator to something, okay, to a function. And if you, I'm not going to follow through all these beta reductions, but at the end, you end up with something like this. You basically created a little generator. You have a universal infinite generator that you had one A, and now you ended up with an A that is followed by whatever you had before. You just created something out of nowhere. So you basically had an A, and now you had another A, and the original thing that you also had, right? So you basically recursed, right? You created one recursion over here. So it's A applied to itself. So factorial, if you could just have something like this, y of this f that is y of f, where f is an anonymous function, then you are capable of doing recursion, okay? And this is impossible for you to understand. I don't expect you to understand. I will try to explain it next week with concrete code in Python. I will recreate the Lambda Calculus in Python, that it becomes a lot more clear. So, but here's the point to take home. It's a model of computation. It's completely different from the Turing machine, as you can see. All right, it has no commonality. It's pure functions. There are no commands, no memory, no machine. There's no machine, right? There's no machine. There's no tape. Okay, there's just symbols, and there's symbolic. There's these lambdas, right, which are basically anonymous functions. That's all you have. You have anonymous functions, and you have the capability of applying anonymous functions to other anonymous functions. There's just functions, and this is the beginning of that. There is no distinction between values and functions. Everything is a function. And values like numbers and booleans and stuff like that are functions too. That, carefully crafted functions that we just decide to give meaning to. That, we want the number 1 and the number 2, so we have functions that represent the number 1 and the number 2. But everything is a function. Numbers are functions. Of course, arithmetic functions are functions that return other functions that represent numbers. So everything is a function. There is no difference between values and functions. And so this idea of functions that take functions as arguments and return functions as the return value, there's nothing else. There's only functions anyway. So everything that is in Lambda Calculus are anonymous functions. That's all. Okay, and the ability of applying anonymous functions to other anonymous functions. So, but the crazy thing is that a few years later, there's the conjecture of what's called Church-Turing thesis, that the two models are equivalent. Basically, everything that you can compute with a Turing machine, you can also compute with the Lambda Calculus and vice versa. It was the inspiration behind Lisp. So Lisp tried to capture the Lambda Calculus and the Lambda expressions. And it's basically the foundational for all functional programming languages, okay? It's basically this idea, everything is a function, even numbers are functions, and the way that computation is that you apply, you apply functions to other functions, and what you get at the end is something that we want to give meaning to, but really it's meaningless. It's just that we want to give meaning for certain things. Okay, so I hope that I have been kind of puzzling you, hopefully, a little bit. I will get back to Lambda Calculus next week, and I will do a little live coding of how to build an entire programming language on top of Lambda Calculus in Python, that becomes a little bit more clear, some of these things, okay?